Okay, let's get started. Can you hear me in the back? Can you hear me way back there? Sound okay? I'll turn it up just a bit. Okay, we're going to have a bit of a shift in topics at this point in today's lecture. We're going to start a 3-lecture sequence on machine learning and deep learning, kind of from the perspective of ECE 408. There's a lot of machine learning courses here in the CS department, in the ECE department, in other departments. So I assume for many of you, this is going to be your second time, your third time being exposed to the things I'm going to say. But that's okay, because I think I'm going to give you a different perspective on things. It's going to be a computational perspective. And hopefully, as you start to piece it all together, the overall ideas behind machine learning make more sense to you. What we're going to do over the 3 lectures is start from the high level, which is our starting point today, and to add detail and add detail and add detail to the point that a week from today, by the end of next Thursday's lecture, we're actually going to write some CUDA code that corresponds to kind of the innermost computational kernels of a deep learning task, a convolutional neural network task. Okay, so for most people, you don't even deal with machine learning at that level because you're using PyTorch or TensorFlow or something where all the details, you don't worry about them. But deep down, the computing has to happen someplace. So our perspective is, well, we want to understand that place. And we're going to kind of get there over today's lecture, Tuesday's lecture, and Thursday's lecture. Okay? So it'll get pretty intense. Now, the end of it all is our project. We have a project in this course. It's an individual project, so each of you will be doing it. And the project is to really take the ideas that we're going to talk about over these 3 lectures and to do it in practice, building a convolutional neural network that you will accelerate using CUDA code that you write. Okay? And you're going to apply optimizations to that CUDA code that you're going to invent them. We're not going to tell you, well, go do this, this, and this. You're going to discover them on your own and compete with each other on a kind of a leaderboard basis to see who can actually develop the fastest running code. Okay? That's the whole idea here. So it's going to be a bit of a journey. For some of you who have seen the material before, hopefully my perspective will be different. And for those of you who have never really been formally introduced to the machine learning concepts, well, good. This is meant for you. Okay? So with that in mind, let me see if I have any. I didn't put the announcements here, but let me just remind everybody, we have an exam coming up October 11th, which is a Tuesday. The exam will be from 7 p.m. until 8:20 p.m. that Tuesday, online, so you don't need to come here. And if you have any sort of conflict with that we need to consider, and we're not going to accommodate every kind of conflict you might have, but if it's a conflict with another course, we'll try to find another time for you. Okay? But we need to know soon so that we can accommodate you. So, yeah, I think that's it. I think that's the big announcement. Any questions, comments, feedback before we get started? Okay, good. You couldn't all hear me? A little concerned my voice is still not there yet. I feel great, but still battling this sinus infection. Okay. All right, so I'd like to put up something that at this point is ancient history, but I think it's so powerful because it's held its ground for almost 30 years, or actually for over 20 years, but not quite 30 years. Back in 1997, a computer scientist, Hans Moravec, kind of put this together that relates the computing power of artificial machines and biological machines. Kind of going back to ancient history from a computing perspective and just plotting things on the trend line. Right? Essentially, we see something that we all have seen before, which is the exponential growth of computing power. Sometimes we call it Moore's Law, sometimes we call it other things. But that's a trend that seems quite steadfast. Even if we extended it to, what's missing because, Moravec did this in 1997, so we could fill in all these, and it would still pretty much track. We're still on that trend. Right? We're now building computing machines, artificial machines, let's say they're as smart as a mouse, or that have as much algorithm or computing complexity as a sophisticated organism like a mouse. That's pretty cool, right? And we can see where this is going. We're a decade, maybe 2 decades away from mirroring what a human might have. So, pretty incredible. You have a question?
Yeah, actually I heard that some neural networks are able to do image classification better than human now.
Yeah, so I think if we isolate it a computer can always do math better than you, right? So if we're talking about specific capabilities, yeah, fine, we exceeded that long ago. But when we talk about general intelligence, we're nowhere near that. But we're getting close, right? And the point that Hans was making is not that, okay, at some point, just because we have the computing power, the machine will be smarter than the man, the human. That's not the point. In fact, what's missing is that even though the hardware has the capability, it's not enough. It's the software, let's call it that still remains to be the vexing problem. But even that, I think we're making some incredible strides on. Right? And the stride I want to point out to you that is the underpinning of all of machine learning and deep learning in the modern era of AI is a very simple idea. So again, before I leave the slide, hey, the computing power is coming. I mean, it's not like at one point in time in the near future, everything's going to flatline. No one is expecting that. I mean, it'll be challenging, but we'll continue to grow. And we are not very far from building a single computer, a single chip, that rivals very complex biological organisms. We're very close to that. Whether that's a good thing or a scary thing, I don't know. The thing that's missing is the software. And on the software side, some key breakthroughs. The next 3 lectures are about those key breakthroughs. And the thing that underlies those key breakthroughs is this. Let me explain it to you slowly. I'm going to talk about the old paradigm, the established way of solving problems with software, which is the way I was taught, which is probably the way you are taught, but maybe not. And the idea is that, okay, as a software developer, we have all these building blocks. We teach you about them in courses. You learn about them in your own projects. You'll continue to learn about them throughout your career. Things like hash tables and sorting and graphs and trees and FFTs and blah, 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 right? These are all things that we know essentially what they are, or we can figure them out, and we use them as components in the code we build. Okay, and that's how computing has gotten to this point. That's how we work. That's the software development process, coding. And you will, for those of you who make a career out of that, you'll get better and better, and so on and so forth at doing that. Now, for the modern systems, the way this works is we take this software, we develop it, version 1.0 in beta, and we test it. It goes out into the real world, and we notice, things don't work, or it fails, or we didn't think about this, or we need a new feature, or blah, blah, blah. And we iterate. And that is kind of the software development life cycle. That's how code is put into the real world. And that iteration process is long and it's expensive. And for certain types of code, like let's say, software that's governing a self-driving vehicle, well, people could die as we loop through that process, or get hurt or injured, or there could be loss. No one wants that. But this is the established way of software development. In fact, it's the established way for engineering, A lot of things we build, whether they're digital or analog, that's kind of the iterative process. By the way, just kind of for your own understanding, most of you are going to be embroiled in this process. You write code, you deploy the code, you fix the code. The better you are as an individual at this part of the loop, the more successful I think you'll be. It's not so much this. We like to focus on this a lot because it's the creative process. It's fun. We do this far less than we do this. And the better you are at this, I think it's just the better you will be as an engineer. Anyway, that's my experience. Okay, so that's the old paradigm. What machine learning and deep learning and AI, which I'm going to tell you right now that the idea of machine learning is different than deep learning. It's different than AI. And I'm going to try to help us understand the difference as I go through this. Okay, so machine learning, let's talk about it as the most general form of this idea of learning. Okay, and we're going to restate the problem. Right? The established paradigm is that, okay, I've got some rules. I see a red light, brake the car. Not brake the car. Slow down the car, decelerate. Okay, and that may have some data, right? The sensor says red light. As I see a traffic light, it's a red light. I create the rule. I write the rule up as some code. Great, I've got the response. Right? That's the established paradigm of developing digital systems. The ML paradigm is different. Here what we're going to do is, I've got some data, red light. I know the answer. Decelerate the car. And what I'm going to do is I'm going to let the system figure out the rules. I mean, clearly the red light is not the only reason you would decelerate the car. There's a lot of other reasons. So we're going to try to generalize all those in this big blob that we won't be able to describe using those building blocks that I told you about before. But rather, if I give it enough data with enough answers, it'll learn itself. It'll figure out what those rules ought to be. That's the new paradigm. And that's what machine learning is about. Okay? Now, if I take a look at a full system, here's an example. There's so many of them. And maybe what I'll do is I'll say that I've got a picture, and what I'm trying to do is figure out in that picture, is there a dog or a cat or a boat or a bird? And what I will do is I will take pictures that have identified dogs and cats and boats and birds, and I'll just put them by volume, by scale, millions of them, into the system so that the system itself figures out the rules for finding the dog or the cat or the bird or the boat. I may never know what inside the system uses to determine all that. Maybe I don't care. But given enough data and the right kind of algorithm for training this thing, that's enough. Okay? And that is essentially what we're going to talk about. Let's go through those details now, right? That is a learning-based system. And the big breakthrough is exactly that I don't know what the rules are. I don't want to code them up. I will let the system learn the rules. Okay, so questions, comments? What I think is very captivating here is that we're just, I think, scratching the surface in terms of using this whole idea of a training loop with a human out of it, right? In the old version, in the old paradigm, I made a very strong point to tell you that, well, you should be in that loop. The problem with humans in the loop is that humans are slow and costly and messy. You know, maybe you quit your job and all of a sudden there's one less human in the loop and we need that human. So humans in the loop by nature are limiting our ability to improve. So the idea that the whole machine learning brings to the table is that we're pulling the human out of the loop and enabling the system to kind of scale on its own. And that idea, that simple idea, applied in machine learning is one example. But that idea, I think, is going to become more and more important in ways we're only yet beginning to discover. Okay? This idea of training, for example, yeah, we can use it to identify dogs and cats and boats and birds. But what if it could also be applied to program, right? What if it could also code in the way that you and I code? And I think these are the areas in which, there's a lot to happen. Anyways, I don't want to get too philosophical about it, but it's quite exciting. Now, just to impress you that It's not just a bunch of academic wishful thinking. Clearly, machine learning is having an impact on the world. In fact, it's not machine learning per se, it's deep learning. And again, I'll define the difference as we go through. Right? Machine learning is general and deep learning is a piece of it. But if we look at silicon, chips that you're using today, like for example in an Apple device, and certainly in the NVIDIA GPUs that we're using in our course, or if you have a Tesla, pieces of this, and you can't see this in the light here, and that's not a big deal, that pieces of this silicon area right here, devoted to deep learning acceleration, the NPU, the neural processing unit. Or if I come to the NVIDIA Ampere architecture, let's see if I can identify them. Right here, this whole area of the silicon devoted to tensor processing. Which, by the way, what do you think tensor processing is? Anyone know? Yeah. It's generalized matrix multiplication. Yeah. So if you're doing, actually it's small matrix multiplication, right here, accelerated directly in the hardware, which by the way is the same thing that's happening here and similar to what's happening there. Yeah.
Do these tensor processing units also have convolution acceleration?
No, they don't. Why not? You don't know the answer to that, but you will. Okay? Yes?
What's the concept of tensor all about? Is there any difference from array, from matrix?
Yeah. In fact, this always used to vex me a bit. Why did we call it a tensor? It's a generalization of a two-dimensional matrix. Let's just leave it at that. Okay, it's a linear algebraic extension. But the operator that we will use almost always with tensors is a two-dimensional vector, matrix vector multiply. Okay, so they are very good at doing that. We're going to get very specific about it, on short format floating point values. Why? We'll get to that. But all these chips, from the Google Tensor Processing Unit, which is now part of the Google Cloud, to the thing that's in your Apple iPhone, to this, to that, is such an important paradigm, we need to accelerate it. Okay? What do you think this Apple NPU is used for? I don't know the answer. What's that? Face ID. Yeah, for sure. Pulling the background out of your images, portrait mode. Yeah.
I know they have a feature where it's able to listen for different, door knocking, alarms.
All of that stuff. Exactly. Siri, just anything where, actually we'll get to it. A series of tasks that we don't have the rules for. But we can learn the rules, given enough data. Okay. I wanted to say this earlier, but let me say it now. I talk to a lot of students, and I find there's two types of students I encounter. There are those students that, I've taken every single machine learning course this university has to offer. I've really embraced it. And then I encounter students that are at the other end of the spectrum, where they're in computer science, they're in ECE, and they want nothing to do with machine learning. And that's fine, okay? But I think you're really you have to come at it, and it's great to come to a conclusion based on information and understanding. But oftentimes, it's reactionary, meaning, everybody loves it so much that I'm just going to take the opposite position and not love it so much. And I think you're doing yourself an incredible disservice. You don't have to like it. You don't have to do a career in it. But in my mind, it's like saying, well, I'm not going to learn sorting. I just refuse to learn it because because I'm weird. I think it's very much like that. Okay, so you have to come to it from a perspective of, I'm just taking one course in it. I'm not choosing to do a career in it. And the reason I say that is because I think it will permeate so much. It's so powerful that it will permeate a lot. In 10 years, we will treat it very much, from the university perspective as we treat fundamental algorithms. Okay? So enough with that. Let's get into the nitty-gritty. Okay. So now let's take this big, fluffy, abstract world of machine learning and let's try to make something very concrete with it. And what we're going to say is there's a bunch of things we can do with machine learning, but here's what we're going to specifically talk about. Like classification. That's probably one of the more basic things that we can do with machine learning, and often successfully. So we've got K categories. Either in my image, there is a bird, or a dog, or a cat, or a boat. And what I want to do is find out which of those K categories my input is in my input, or my input belongs to. Okay, this is a basic classification task. We also have a regression task. Let's call it the continuous version of the classification task. Where what I want to do now is not bird, cat, boat, dog, but rather what's tomorrow's temperature. Meaning I'm trying to predict a continuous value of something. Instead of n discrete, it's continuous. The techniques we're going to use for classification and regression, as you can imagine, are largely similar, or they have a lot of similarities. Okay? And those two, I think, if you understand those two, the rest of these machine learning tasks tend to follow. So we're going to talk a lot about those two and less about the other ones. But just for sake of completeness, we can have transcription tasks where we're converting a sequence of input from one form to another. And it's not machine transcription per se, but let's call it fuzzy transcription. Things like I'm converting from Chinese to English or Spanish to German, where it's not so straightforward. There's not one right answer. Okay. Actually, I guess transcription was, transcription and translation are often similar. But then a few other tasks, just for sake of completeness: forecasting, recommendation, anomaly detection, ... We're going to focus on classification. And I want to do a deep dive on it so that we all can be kind of rooted in something concrete in terms of what we're trying to accomplish. Okay. Another question that I'm going to keep coming back to is why now? Why did this happen now and not before? In fact, I would say the rise of machine learning, we can actually pinpoint it to 2012. And I'll explain why, probably on Tuesday. But so it's a very recent thing, and it's not because we invented machine learning or deep learning in 2012. No, there were a lot of advances that were coming up for many, many years. But kind of a lot of things came together in the recent past, 2012 being the recent past, where all of a sudden it's now working. It's now working. So why now? Part of it is that the concepts like backpropagation and deep models, and then soon frameworks like PyTorch and TensorFlow, have really made the stuff super accessible. My son, who is in high school, is in 9th grade, even he, the other day, downloaded PyTorch. So the idea that these frameworks are accessible by a huge fraction of humanity now is just incredibly powerful. So that's part of it, computing power. And that's why we're here, right, in this course, because the fact is that we can't, it's not enough to have PyTorch. We must have the computing power. So GPUs have been essential to the rise of deep learning. And then the last thing is data. And really the three of these things kind of came together at the right point in time to really give us this, I think, very exciting new turn in the world of computing. Deep learning happened in part because of the computing power. The computing power came in part because deep learning needed the computing power. We're collecting lots of data with cheap sensors that are basically everywhere with cloud storage because we can do stuff with that data, right? So the three things are combining together in a way, in a virtuous way, to really enable this technology now. It wasn't the case more than 10 years ago. It certainly is the case now, right? And because of all that, things are happening not just for autonomous vehicles and smart devices, but across so many aspects of our society today. So it's really an incredible time to be working in this area. So before I move on, any questions? I'm working towards getting us to start diving deeper. It's all general stuff at the moment. Any comments?
Transcription basically just a type of classification?
Is transcription a type of classification? Yeah, it could be, because one classical type of transcription is character recognition. Or digit recognition, so I write some digits, I want to be able to recognize them. And that's a classification task at that low level. But as we generalize it, maybe not so much. It takes on a different form. Yeah.
So for like an everyday user, are these like algorithms able?
Well, it depends. There are some deep learning tasks that everyday users use that you don't need a GPU for. One that I'm very familiar with is if you've ever used a Zoom meeting and you've blurred your background or replaced your background. That's deep learning. It's a convolutional neural network, similar to what we're going to do here, that I think you don't need a GPU to have that accelerated. It runs on your CPU. You don't even know it's deep learning, but it's deep learning. Is that what you're asking? Yeah. But by and large, a lot of this deep learning that we encounter is either hardware accelerated, like on the Apple A14 neural processor, or it's accelerated on a GPU. Okay, so let me kind of zoom through this a bit. So let's take applications and let's try to talk about them on two bases. There's things that are, how hard are they to perform, and how hard are they to describe? Okay, so things that are easy to perform, things that are hard to perform, things that are easy to describe, things that are hard to describe. And yeah, I hate to say it, but our ECE 408 MPs and labs are at the corner of that continuum, right? They're easy to describe, thankfully for us, and easy to perform, thankfully for you, even though you don't realize it. Now, we used to think things like chess were the pinnacle of machine intelligence. Because, well, they're hard to perform. How do you build a chess-playing program that does well? And over time, we actually built up the rules because it's so formally easy to define that we are now able to build things that play chess because the rules can be codified and the trees can be searched better than a human can. Okay. But there's a whole array of things that are hard to describe but easy to perform. Right? I mean, recognizing faces seems like it should be very easy. We do it without even consciously devoting any effort to it. But it's hard to describe all the rules associated with doing that. So the point I wanted to make here, and by the way, there's some things that are just hard to perform and hard to describe, like international diplomacy, or policy, public policy, or literary analysis, or strategy, right? And those are where general intelligence, techniques will come. Kind of the frontier for us is really to take these things that we suspect to be easy to perform and find ways to do them. Okay, that's the frontier that we're at right now. Sorry, I'm just going to skip through things here just a bit. And I don't want to rehash so much. So when we deal with these kind of problems, we often will talk about this idea of feature. Okay? And in fact, when I first dealt with machine learning, when I was a student, this idea of feature kept bothering me. Like, what is a feature? I don't understand feature. But we throw around that word so often that I felt I was confused. So, but a lot of machine learning is based on this idea of feature. And in fact, if we look at the evolution of it, we started with these systems that were really based on rules. Like if we were building a program to play chess, we would hand design that program based on the rules of chess and the strategies employed by people who are good at chess, and then put some, tree search algorithms around it, but primarily being rule-based. And then we evolved into the machine learning world where now it's not so much about the rules, but about features. So what is a feature? Well, in the world of in the world of chess, let's say, a feature might be the board positions of all the pieces. So the position of the king or the queen or the queen's rook, whatever it might be, are all features of the board. And based on those individual features, we can craft some strategy around how to play the game. So the world of machine learning is really about identifying those features where you and I, as the developer, are finding those features and then letting the data drive how those features are important. Okay, again, I'm trying to take us a little further along here. So we're going to focus on this for the moment, okay? The idea being machine learning is really about identifying those features and then letting the data drive how those features help us on the task we're trying to perform. What then we'll show you is that there's another column here called deep learning that's actually different than machine learning. It's an evolution of machine learning where we don't worry so much about those features. We let the system find those features and kind of normalize those features, remap those features so that we can do even better on the output. Okay, so let's start here in terms of classical machine learning. So what I would encourage you to do is become familiar with kind of the workhorses of classical machine learning. We're going to talk about a few of these in detail. Okay, but the classical machine learning repertoire has things like naive Bayes, or perceptrons, or linear/logistic regression, support vector machines, decision trees, clustering. If you take a machine learning course, you'll go into the specifics of these techniques and the mathematical underpinnings of them. And they're good. The idea here is that we prescribe the features of the system, and those features are somehow combined together through the various techniques like linear regression to help us identify what the output should be. Okay, so for example, let's say we're trying to build a regressor model, a linear regressor, that's trying to predict tomorrow's temperature. So we need to provide some input features into the model. The features might be the last week's worth of highs and lows, right? 14 data points. High temperature a week ago today, high temperature 6 days ago today, ... And those 14 data points are then combined together in such a way to build a predictor for tomorrow's temperature. Right? And that is a classical linear regression model. And we can build, we can learn about all these things, which, by the way, is, multiple decades worth of breakthroughs and come up with models that work pretty well. Right? That was the state of machine learning for a very, very long time before this whole idea of deep learning came to the table about 10 years ago, 2012. And so what I would encourage you to do, right, if you really want to see if there's anything here, whether you take a course on this stuff or whether you learn it on your own, these ideas are very simple, and the math behind them is accessible by all of you. You just have to give yourself some time to get comfortable with the ideas. They're not very hard. The ideas center around the following concept. Okay, let's say we're trying to build a algorithm, right? Some code that's going to tell us the blue dots from the green, the blue circles from the green triangles. Obviously, we're not telling you whether a data point is blue or green or a triangle or circle. We're just telling you the XY coordinates of it. We don't know, we don't see this diagram at first. Right? In fact, it could be a multi-dimensional, 20-dimensional diagram that it's not easy for us to visualize it. I've just made it simple here to make a point. Right? All of the techniques I showed you on that previous slide can attempt at this classification problem. It is a classification problem. I give you a data point, I give you its XY coordinates, you tell me whether it's a blue circle or a green triangle. Right? That's the task. So the general approach that all of these learning techniques are going to use is they're going to try to create linear models, combinations of linear models. So maybe if I drew a line, that red line, that's going to help. Right? Clearly, as a human, I could draw that line, and yeah, I'm going to get a boundary where on one side of the boundary, they're all green. On the other side of the boundary, they're green and blue. Well, that's pretty helpful. So let's draw that. And I can come up with the equation for that line, the linear equation for that line. The techniques I showed you on the previous slide, in one form or another, are trying to discover these linear classifiers that help us. Clearly, one is not enough. Maybe I can draw another one, and another one, and another one, right? So the idea with machine learning is I give you the data and I give you some examples where for each XY, I tell you whether it's green or blue, and we let the algorithm find these red lines so that at some point we get pretty accurate about identifying red from blue. Actually, the particular model here is a decision tree. Right? Because we've drawn a bunch of these things and we've divided the space based on these linear models. Sounds good. We can, with enough of these things, we can get very accurate. Okay. Now, for a very long time, that was the state of the art. That was machine learning. And it did quite well for a lot of things. Didn't do so well at like Face ID. Right? We would never use the simple model for Face ID because getting to 98% or 90% is not good enough, right? We have to get to 99.9% in order for Face ID to be good enough for Apple or Google. So they could do a lot of things pretty well. You know, like a lot of financial companies probably use these kind of models to help plan retirement portfolios. But to get to the next level, clearly they're not good enough. Now, part of the problem is the models can't do a shift of data representation. Meaning, hey, if I could just remap everything into r theta as opposed to xy, all of a sudden the data becomes trivially separable. Okay, so it's not that every problem will be amenable to this kind of a shift in data representation, but oftentimes almost every problem needs a shift in data representation in order for us to make it tractable. So we take all those techniques that I put on that previous slide and we think about, well, why do they fail? Okay? And they fail because they're complex, they can learn a lot, they can find those red lines pretty effectively, but they're not yet capable to do data representation shifts so that we can make the problem easier, right? By the way, as humans, like when we solve problems, those of us that can solve puzzles faster or solve problems faster are often good at these shifts, these abstract shifts in the problem. So when we go from machine learning to deep learning, what we're going to discover is that by adding additional layers to the model, the upper layers of the network that we're introducing, what they're really doing is they're shifting the data in such a way that the lower layers, which are, the classical machine learning processes, they're able to be much more effective. And oftentimes, these shifts in data representation are the hardest part. Okay? So that's to come. The other part of it is that, boy, how do we know what a feature is? And, for a very long time, when I was a graduate student taking a computer vision course, it was all about features. Like, if we're looking for human faces, what are the landmarks that we should be looking for on a human face? Is it the corner of the eyes? Is it the shape of the nose? Well, what if the person's wearing sunglasses? What if their nose is occluded by their hand or their phone? Can we still recognize the face? What about the corners of the mouth? So the problem with machine learning for a very long time became dealing with features. What are the right features? And what do we do if features are in some way in the wrong scale, in the wrong color, in the wrong representation, they're obscured, occluded, ... Okay, so, and then they also become very specific. The things I use for text are different than things I use for audio, and so on and so forth. But that's what machine learning was all about, is really finding features that were robust. Right, and this is just putting on a slide what I just said, that if I'm thinking about the features that I'm going to put into and code into my machine learning, I have to really think hard about the right feature set. Features and data representation, those limited the performance of machine learning. Deep learning kind of breaks through that limitation. And we're going to talk about that on Tuesday. But for today, let's continue with understanding specifically these classical approaches. Okay, any questions? Because it's a bit long in the intro. I want to start talking about specifics. Now is a good time to ask general questions. If you've ever had a general question, something seemed confusing, maybe I can try to clarify it for you. Yeah.
say we're training them, like, I mean, this point's probably different, but when we train a model, is that just like changing the coefficients on different, not, I was about to say features, but on like different, I want to say, like discriminators between one
Yes,
place and another?
absolutely. Not specifically for a decision tree. Decision tree will create new separators. Okay, but in general, when we use one of these classic models, there's a bunch of parameters. For example, the slopes of the lines. What should the slopes of the lines be? Those are learned based on what the data tell us. Okay, so indeed, yeah, we're learning those XY slopes and intercepts. Yes?
This is probably too too far ahead. We're probably going to cover this later. But how does a convolutional layer in a neural network help with classification? Why do we need convolution?
Yes. Why do we need a convolutional layer? I'm going to try to answer this again later, more deeply, but let me just say, remember the idea that a convolution essentially is a filter for a kind of feature. Okay, right? If I wanted, remember I gave an example of a filter that found a vertical line in an image, a grayscale image, right? Now, I was looking for a vertical line, and that was the filter I created. So it helped me find, a vertical line in I don't remember whether it was 5 by 5 or 7 by 7 patch of an image. Now let's say I don't know what the filter is. I don't know the feature that I'm looking for. I'm just looking for human faces. I don't know whether I should be looking for this filter or that. The convolutional layer that I'm going to learn will figure out the filter, will figure out the feature that I'm looking for. I don't know what it is because I can't think of any good ones. Does that make sense? Yeah.
So, for people who don't have that much ML background, the question is, so you've already shown a bunch of the diagrams. So we have a layered approach to our models or to the process.
I haven't actually said layers yet, but yes, layers.
Oh, well, you did now.
Okay.
So we have layers. So a question is, why do we do that? Why do we have different layers compute different solutions?
Yeah. So let me just bypass the question a bit by saying, remember how I said I don't know what the features are. Features are a pain in the butt because it never seem good enough if I come up with them myself. And I have this problem with data representation. So the fact by having multiple layers, which I will get to, what these layers accomplish is finding the features and putting them into a uniform representation space that maximizes my chances of doing the right thing at the output. Okay, that's why we had layers. Yes?
I still don't really get why representation matters. So let's say you change your representation, wouldn't that just be a different way of presenting the same data? So the data is the same, the representation is different. If you train one set of data versus the other, won't that settle down at the same equilibrium eventually?
Well, no, because I'll give you the very simple example, right? So trying to identify blue versus green here with lines, with enough lines, I can approximate it. Maybe I'll get it wrong at the edges, okay? Now, but if I could shift to this representation, it'll be much easier, right? The problem is, I don't know this representation a priori. I could, as a human, try to pick everything apart and understand the dynamics of the data and maybe come up with it on my own. Or we can let the learning system figure it out. Okay? Right? That's a complex, nonlinear relationship. And the learning system can figure these things out. Well, let's let it do it. Okay.
So So the goal is to get the system to figure out the representation.
Yes, yes. I'm providing it input, in this case just x and y points, but it does the remapping internally somehow. Okay, so let's move on. Okay, so I'm going to introduce a task. The task here is classification. Formally, I've got a function that takes an input, let's call it a real valued input, and maps it into one of k categories. Okay, so I take my input of some dimension n, and I'm going to put it through this classification function f. So the input vector is x, n dimensions. And my classification function has some set of parameters, theta. I don't know what they are. From our previous diagram, those lines. Let's say my classifier, I can put 3 lines. Right? My classifier will create 3 lines to separate the green from the blue, and those 3 lines are described entirely by theta. That's the idea. Okay? I don't know what theta, I don't know what those lines are. I know there are 3 of them. I'm just going to make it simple. And we need to go figure out what theta should be. Right? Theta, specifically in this case, if I have 3 lines, I need to be able to have 3 general lines in a 2D plane, which means I need 6 parameters to encode those 3 lines. Make sense? So there we go. That is a classifier that's going to use 3 vectors that I'm going to learn. We can approach this, we're going to start with the idea of a perceptron. I could have chosen any one of those classical machine learning concepts on that slide, but I'm going to pick perceptron. And the reason I'm going to pick perceptron, it's because it's the building block for a lot of things in deep learning. Okay, and the idea of a perceptron is very simple. It's a single element, and that element can take, so it's not 3 lines, it's going to be just a single element where it takes let's see here. So we're going to have f as I described, where essentially we're going to take x, so we've got x1 through xn, here's x, and I'm going to multiply each x by some weight, w through wn, and I'm going to add to that, I'm going to sum those up and add to it some scalar offset, b, the bias. Okay, so I can rewrite that whole thing by this multidimensional linear equation. It's multidimensional because I've got x1 through xn, which means I need to have w1 through wn. I multiply all those, I do a dot product on those 2 things because that's the way this thing works. I multiply each w by each x, and then sum them all together. That's a dot product. And then I add in the scalar value b, right? It's a dot product of n dimensions plus a single scalar addition. That is the core of this model, the perceptron. And by the way, this perceptron model was inspired by the biological model for a neuron. As far as we know, that's the way this neuron operates, this biological entity. We also insert into it a thresholding function here at the very last end. which in its simplest form, in the way this perceptron was proposed, is the sign of the output. If the value is negative, it's 0. If the value is positive, or 0, or positive, if the value is greater than 0, it's 1. So it's just a threshold based on whether the value is greater than 0 or not. Okay? So there we go. Basic building block. Now what can we do with this perceptron? So can we, for example, learn the XOR function with a single perceptron? You remember the XOR function, right? If I've got an input, a two-valued input, meaning I've got x1 and x2, where x1 can be 0 or 1, and x2 can be 0 or 1. The output will either be a blue dot or a green dot based on whether x1 equals 1, or I'm sorry, let me call it x0 and x1. Based on whether x1 and x2 are the same, right? If x1 and x2 are the same, we get a green dot. If x1 and x2 are different, x0 and x1 are different, then we get a blue dot. So we want to know, hey, can we learn XOR with a single perceptron? And we work it through, and we try, and maybe we look at a bunch of data, and we try to make things work, and we realize, no, it doesn't work. I'm not going to go through the example, but you can. It's in the slides. Right? Basically, what I'm trying to do is I'm trying to see if I can put a weight, right? These are the weights on x0 and x1 in such a way that I get this to work. I can do an AND function. The AND function is just x0 plus x1 minus 1.5. That's greater than 0. We've got the AND function. The OR function is x1 plus x0 plus x1. No weights, right? The weight on both of these is 1. And the bias is minus 0.5 in the case of the OR. So I can try to combine them together, but I can't get the XOR to work. So in order for us to get XOR to work, what I need to do is I need to create two layers. I need to have the AND perceptron here, the OR perceptron here, and then I need to combine the two of them to create the output in this particular case. Okay, so a single perceptron is not enough. But if I can array them together like this, yeah, then I can get to where I need to be. This is another way of me putting those green triangles and those blue dots on the screen and saying, I've only got 3 vectors that I can draw. Yeah, if I had a 4th vector, I'm going to get better. If I only have 1 layer of perceptrons, I'm not going to be able to do XOR completely. I need to add another layer in order for us to completely describe the XOR function. Okay? So I got to build enough complexity in my system through this layering in order to capture the nonlinearity of the problem that I'm trying to model. Okay? AND is a linear function, 1 perceptron's enough. OR is a linear function, 1 perceptron's enough. XOR, nonlinear. I need 2 vectors. got to have another layer. And that brings up the multi-layer perceptron, MLP, multi-layer perceptron. And we're going to talk extensively about the multi-layer perceptron because it's quite effective at doing things like handwritten digit recognition. So what I can do is I can take a bunch of these perceptrons and, I mean a lot, not just a few, a lot, and put them into, let's say, 2 or 3 layers to do things like handwritten digit recognition pretty well, like upper 90s percentile, upper 90 percentage in terms of accuracy, pretty accurate, probably as good as a human. Okay, and the idea with a multi-layer perceptron is, like in the previous slide, I'm just arraying these together where the output of one layer is fed into the input of another layer. Okay? So in the case of this multi-layer perceptron, we'll come back to this. What I'm doing is I'm going to take some input. Let's say I've got a 28 by 28 image. Okay? And that's just a little tiny image, grayscale image of a digit. So it's 784 pixels. So I take those pixels and I just represent them as the input array. Pixel 1 all the way to pixel 784. Okay? And those are the inputs. That's my input layer. Here's a set of perceptrons. And what I do in that second layer or hidden layer is I have 10 nodes in that. So this is what we'll call the input layer with 784 nodes. I've got a hidden layer with 10 nodes. And then I've got an output layer with 10 nodes, where those 10 nodes correspond to, is this a 1? Is it a 0? Is it a 7? Is it a 9? Okay, so I could set that up just using kind of the idea of a perceptron like I showed you on the previous slide. What we don't know is what are all the weights and what are all the biases associated with this particular multi-layer perceptron. I don't know what they are. As a human, there's no way I could describe them to you. Right? There's no, but we'll learn them. And that's really what we're going to talk about here. Okay? So let's generalize. We've got a linear system we can build, right? That's the single perceptron. Some number of inputs get combined to produce the output Y. We can generalize this by saying I've got some input layer with some number of inputs, could be 3, could be 784, could be 1,000,000. At this point, it doesn't matter. I've got another layer where those inputs go into that layer, and each input connects to some number of the, each node here connects to some number of the inputs. We often will talk about a fully connected perceptron, where each node is fully connected to all the inputs. It's the most general form. So if I have 3 inputs, each of these in this layer is connected to 3 inputs, meaning it's going to have 3 weights. How much I should weight x0, how much I should weight x1, how much I should weight x2 in terms of generating the output for this particular node. Right? And then I also have a bias, a B. So 3 weights and a bias for each of these. Again, I don't know what they are, but I'll learn them. We call those parameters, right? And you can see, right, that if I have something this complex, I've got almost 8,000 parameters. There's no way a human can generate what should be a good setting for 8,000 values like that. But we will learn them. We will learn through this process that I will tell you about shortly. Okay. And that's all machine learning and deep learning is about, is really figuring out what those parameters should be to maximize the performance on the output task. Okay, so maybe I'll stop here, right? This is just a generalization again. We have the input layer, we have the hidden layers, we have the output layer. We've got weights and biases, and we're trying to figure out which of the output is most likely. Should we have K0? Should we have K1? Should we have K2, 3, ... We have digits, we've got 10. So what this encodes at the output layer, K, what K represents is the probability that the input, X, is in class K sub I. Right? Remember, this is a classification task. So what we'll do is we'll use this function argmax, which says, hey, which of these is the highest? Just tell us what the I is. Is it a 0? Is it a 1? Is it a 2? Is it a 3? Is it a 9? Okay. All right, let's stop here. And when we come back Tuesday, we'll talk about how to train this thing. But before we go, any questions? Yeah.
This is more relevant to sort of the first part of the lecture, but I was just curious, why do we still use like NVIDIA GPUs for deep learning if they're potentially like ASICs that are better optimized?
Because you have to go and buy that ASIC.
So do you think that'll like change going into the next few decades?
Well, I mean, you have a phone. Your phone has an ASIC. It's the, let's say it's the Apple A14. That's better than an NVIDIA GPU for your phone, right? So you did buy an ASIC with, that's better than a GPU, right? So for special purposes, of course, we're going to buy ASICs that have neural accelerators in them. Does that make sense? Yeah. Okay, let's talk on Tuesday next week. Thank you.
I have some.